afternoon, everyone. Welcome to this first colloquium. It's my great pleasure to introduce our esteemed speaker today, Professor Yaroslav Sergeev. Okay, I don't know how to pronounce it right. Professor Sergeev is distinguished professor at the University of Calabria in Italy, where he leads the numerical calculus lab. He is also an affiliated faculty member at the Center for Applied Optimization at the University of Florida. Professor Sergeev has made significant contributions to the field of global optimization. Notably, his pioneer work in infinity computing and calculus has opened new avenue in optimization techniques. Today, Professor Sergeev will give us a talk titled Problems, Methods, and Applications in Lipschitz Global Optimization. So let's welcome.
Do you hear me? Okay, thank you. So thank you very much for invitation and for this kind of introduction. So the topic of today is problems, methods, and applications in Lipschitz global optimization. Lipschitz global optimization is my first love in applied mathematics and in mathematics in general. And on March 7th, there will be my second talk in Tsinghua University about infinity computing that you have already mentioned. And that talk will be even for a broader audience than this one. But also, I am sure that this topic will be clear for everybody, because I'll try to mainly to talk about ideas presenting pictures and not technicalities that can be read from my books and papers. So this is the outline. First, we will talk about what is Lipschitz global optimization and describe these kind of algorithms, presenting some ideas starting from one-dimensional algorithms and go into multi-dimensions. Then we will talk about some applications, and after that, some new ideas, more or less new ideas that can be used to compare deterministic, for example, and stochastic algorithms. You know that nowadays meteoristics are very popular, and people in mathematical programming say, no, this doesn't work, this is not interesting, no convergence. People from meteoristics say, we solve real problems, and you play games. So let us see how it is possible to understand what is better, what is worse, if something is better and something is worse. As you can understand already from this phrase, there will not be a winner in this way. Okay, so let us start. The problem that we consider is this one in general. We would like to minimize a function f of x over a hyperinterval. So we consider at the moment here only box constraints. Even though we work with multi-extremal constraints, in this lecture I will not talk about. The only information that we know about the functions that it satisfies this Lipschitz condition with the Lipschitz constant L. And the function can be first multi-extremal. This is the main feature that we have. So it can have many local minima and also can have several global minima. For example, this problem, you can see it has a local minimum that has a very huge region of attraction that would be bad for some local methods, because every methods from many starting points will find this one, whereas the global solution, global minimum, is in this other region. Then what we can say, that the function can be non-differentiable. So all gradient methods are not cannot be applied here. Then black box. What does it mean, black box? This means that the function is given by a procedure and you do not know its analytical representation. And this means that interval analysis techniques, for example, cannot be applied. Then the function can be such that the Lipschitz constant is unknown. And in addition, each evaluation of the function is a time-consuming operation. When I started to work in such kind of problems, people told me that this is impossible to attack these kind of problems because they are too complicated. Nevertheless, I was able to construct my career on these problems. Okay, so I always would like to show the pictures of heroes, and obviously hero of this talk is Rudolf Otto Sigismund Lipschitz. What kind of methods will we deal with? So suppose that our hyperinterval is subdivided in some subregions. At each subregion, we have some points, a set of points where we have evaluated the objective function, and then there are some parameters. So the first step in all the algorithms will be to estimate somehow the Lipschitz constant, then to calculate characteristic R for each subregion. This is a kind of goodness from the point of view of a possible location of the global solution in this subregion. Then we take the best characteristics, namely the corresponding to the best subregion, and evaluate new points. And of course, somehow we have a stopping rule. So all the algorithms will be like this. Now, you can see that there are many books that we have published with our methods, and we have organized also some conferences where we talked about this global optimization, and not only global, but also numerical computations. You will find the most of the ideas I will talk about in this book, and also on my webpage, many papers can be downloaded. So the main problem in Lipschitz global optimization is how to estimate the Lipschitz constant, because this is the only information really we have from our objective function. And there are several ideas. The first idea is to take an overestimate of L and to use this overestimate somehow in numerical algorithms. The only problem is that the complexity of finding such an overestimate is the same as the complexity of finding the global solution. So it is not, very often it is not clear from where to take this. In some cases it is possible, but in general this continues to remain a good theoretical tool, but not practical one. In practice, people often to use some adaptive estimate of the Lipschitz constant. For example, people started with the global, so-called global estimates. This means that the same estimate is used in the whole search region. But if there are subregions where local Lipschitz constants are different, one is huge, another one small, then it would be nice to propose methods that are able to understand this and to balance local and global information. As we will see, this, if you are, one is able to do this, then this results in a huge acceleration of the search. And then it is possible to work contemporary with all possible Lipschitz constants. So nowadays there are these four main ideas, and all methods in Lipschitz global optimization use one of these ideas. Remember that evaluation of the function is a time-consuming operations. So very often people measure the speed of the methods in these terms. So how many function evaluations a method has done before the execution of the stopping rule. Okay, let us discuss all these four ideas and some other ideas step by step. So the first method that has been proposed, and people continue to propose it continuously. I'm in several editorial boards of different journals, and people reinvent this method. I say that people like to write, not to read. Okay, so this idea has been proposed by Piavsky in the 70s. So suppose that we have these 3 points, we evaluate the function at these 3 points, then the objective function should be above inside each of these intervals. It should be above these umbrellas that are given, the slope of which is given by Lipschitz constant. Okay, so the function cannot go, due to the Lipschitz condition, below these umbrellas. Okay, so from there we can have a method. We have the search region, we subdivide it in subregion, construct one umbrella in each of them, and where this value that is clearly the lower bound of the function over this subinterval, where this value is smaller, we subdivide this subregion and continue our search. Okay. However, we can immediately notice that our function is continuous, and this minorand is not continuous. So the question is it possible to propose a continuous minorand? The answer is yes, and this is the answer. We take one point, evaluate the function, construct this race, and then we take another point and evaluate in this point and consider not right-hand side, but left-hand side. And so we obtain this great zone. So the function to arrive from here to here should be inside the gray zone that is delimited by race using the Lipschitz constant. So immediately we can say that the value R is the minorand for the objective function, for the low bound, for the objective function, and also for minimum of this minorand over the interval, this considered interval. The objective function cannot go below than this. And from there, we obtain Pijavsky method. If we know the Lipschitz constant, we do like this. We construct the minorand and decide to evaluate the objective function in the point corresponding to the minimum of the minorand. And then this means that we are able to improve our minorand. And then we evaluate again in the point corresponding to the minimum of the minorand and improve again and improve again. So it is clear that this piecewise linear minorand will be closer and closer to the objective function, and we will be able to obtain lower and upper bound. So upper bound clearly is this, the minimum value of the objective function where we have evaluated. And this is the low bound. So the global minimum should be between these values. Okay. So this is the first idea. The second idea was an adaptive estimate of this Lipschitz constant. I will skip this, how it can be done. It is not complicated. What I would like to say is that if we work with this objective function, then the methods using the global Lipschitz constant will be very slow here. Why? Look, this function is special because it is a wide interval where there is the global solution, and over this interval, the local Lipschitz constant is very low. But over this interval, CB, it is very high, but it corresponds to the global maximum. We are not interested in it. But if the method uses the global Lipschitz constant, then it will use this value. So the method will think that also here the function goes with these pulsations. And this is not good, obviously. So it is nice to balance local and global information. And we have proposed several techniques that automatically allow the method to understand that here it is possible to go faster. And this results in the fact that the constructed minorand is closer to the objective function. And this means that there will be acceleration. Why? Look, if we consider the black minorand corresponding to the global Lipschitz constant, then the next evaluation of the objective function will be at this point here. But as you can see, the global optimum is in the other region. If you use the red one, then it will be here evaluation. This will be the minimum of the minorand. And so we will be closer, and the algorithm, we will not evaluate in this interval the objective function. This will result in an acceleration that is pretty big. For example, here you can see that we have several methods, okay? And this method is with the local balancing techniques, or as we say, local tuning techniques. That is many times faster than previously proposed algorithms. And this is the maximal speed up, and this is the minimal speed up on a set test of 20 functions from the literature. Okay. There is an interesting subclass of these Lipschitz global optimization problems where not only the function, but also its first derivative is Lipschitz. But again, it is bad, so it can be multi-extremal and all this kind of stuff. So the question is, if we know that the first derivative is Lipschitzian, is it possible for this smooth function to construct some minorant that is better than this one, that is piecewise linear, so non-differentiable in certain points? First of all, people tried to use the additional information about the derivative, and Gergel and Breiman and Cutler have constructed these minorants. They are not piecewise linear, but piecewise quadratic. However, you can see that first, sometimes this quadratic is worse than linear. And then it is also non-differentiable in some points. Is it possible to do better? The answer is yes. And this is my paper in mathematical programming many, many years ago. So it is possible to notice that what is the Lipschitz constant for the derivative? This is the maximal curvature of the function. So if we consider these gray triangles, then it is possible to prove that the function cannot go inside. Why? Because starting from here, and if it goes here to return and to arrive to this point, its curvature should be higher than the Lipschitz constant. And this is impossible. Unfortunately, we do not know what are the points in which this parabola touches in each subinterval the minorant, the non-differentiable minorant. Once again, fortunately, it is possible to find explicitly these points, solving a system of two quadratic and two linear equations, and to define these points. This allows us to construct this nice smooth minorant that obviously allows one to accelerate the search significantly because it is significantly better than both minorants considered so far. Okay. It is possible even in the class of functions with Lipschitz derivatives to find another subclass that can give another acceleration. This is our fresh paper with Professor Pasypkin, who is the director of the Federal Russian Center of Computer Science in Moscow. So this is a huge, very huge institute. So this is the condition. So in the Lipschitz functions, we have here L and here minus L. But if the function can decrease and increase with different slopes, this means that alpha is not equal to minus L, for example, but and they are not equal. Alpha could be higher. Then this can be very useful. Of course, Lipschitz and the interval Lipschitz are connected, but if alpha and beta are significantly different, this is very good. And this is also very good if the derivative satisfies not Lipschitz but interval Lipschitz condition. I show you an example. Suppose that this is derivative, so its maximal slope in decreasing is -3, but it increases only as 1. And the function corresponding to this derivative is this one. And in this case, it is possible to construct methods that give significantly better minorants and majorants. For example, this is Lipschitz ones and this is new ones. And there exist cases where they differ strongly. Okay? So, as usual, if we have more information, we can use it and construct more efficient algorithms. Well, now let us go and to think about multidimensional generalizations. How can we solve multidimensional problems? We start, I recall that we started with these umbrellas, and these umbrellas in multi-dimensions will be cones, obviously. So if we have evaluated the function in the point C1, and we have obtained f of C1, then the objective function should be above this cone that has the slope of Lipschitz, defined by the Lipschitz constant. If we have two cones, then the function should be above the intersection of these two cones. If we have three, about the intersection of three cones. So it is possible to show that very quickly it becomes computationally intractable to find the intersections of all these cones. And so it is necessary to invent something different. First, it is possible to reduce the multidimensional problem to a family of nested one-dimensional problems. So how do we do this? We fix some coordinates in x1, and we minimize three problems in the coordinate x2. Then we decide by the same method at which new point to evaluate the objective function. We fix again and continue. So here we have many sub-problems that have their birth and death during the search. So this kind of stuff is very good for parallel computation, because you can give jobs to many different parallel computers. Another idea is, you remember that here in one dimension, we do not construct cones everywhere, only for small subregions. One subregion, one cone. But we can do this also in the multidimensional space. So we have this subregion, we evaluate the function in the central point. Here we have the cone, and this will be the minorant, the low bound for the function over this region. Then we can proceed like this. So this is the search region. We evaluate in the central point. Then we subdivide in each of new points. We evaluate the function once again. Then once again subdivide, once again subdivide, and so on. So more or less the same as it was in Pijavsky, but moved to the multi-dimensions. Okay. So this is central sampling approach. For each subregion, we evaluate only once. There is another idea with regard to the search of the Lipschitz constant. This idea is fourth idea of John Sperton and Stuckman. So they have proposed to consider this diagram. So here on the axis, we have half of the diagonal of our search region. So this value, AC, for example, okay? And at the point A, we have the value at the central point, so here. Then it is possible to prove that the intersection of the ray with the Lipschitz constant is exactly the low bound for the function over this search region. So they propose to put all the intervals in this diagram, and then it is clear that at the next iteration, it is necessary to subdivide interval A because it has the smallest low bound, okay? This if we know the Lipschitz constant, but we do not know it. So probably the real Lipschitz constant is this, and then the interval C will be the best one, okay? Jones and colleagues have proposed to subdivide all the intervals corresponding to a possible best value. They will be finite. And the nice idea is that we do not know which of these intervals corresponds to the real Lipschitz constant. But we do know that among these intervals, there is one corresponding to the right one. So this is a brilliant idea. And but there is a price to pay. The previous methods had global or local convergence. This means that the sequence of trial points produced by the algorithm converge either to global minimum or to local ones. Here we have everywhere dense convergence. So the method will converge to all the points of the search region. But since we are not able to execute infinitely many operations, we consider only a finite number of points. This method works pretty well. Okay. Another idea is not to subdivide our hyperinterval in sub-boxes, but in simplices. Then, obviously, this allows to obtain better low bounds, but it takes more difficult programming. And you see that here you evaluate not in one point for each subregion, but in all the vertices. So in n+1, where n is the dimension vertices for each subregion. Okay. Another idea. You remember that Pijavsky has proposed not to use 1 point, but to use 2 points. And this was resulting in good methods. But also in multi-dimensions, probably n+1 evaluations is too much. 1 evaluation is too small. So let us take 2 cones for each sub-box. Then this will be the low bound for the objective function over this subregion. And Pinter has shown that this can be done. And we then have shown that it is even not necessary to construct cones. It is possible to walk over diagonal. So this is more or less as in 1 dimension, and to obtain these low bounds in the same way. Now, when you have a diagonal method, you have the second problem. So the problem is how to subdivide in some boxes. You should evaluate the function in each subbox. So this was IB we have evaluated initially. Then by hyperplane we have subdivided this box into subboxes and have evaluated here and here new points during the first iteration. It seems that everything is fine, but it is not. So this simple subdivision strategy leads to the following effect. If we, during the second iteration, have evaluated here, and during the third, we will be probably obtain points that are very close one to another, but the method does not understand this because they were produced during different iterations. Okay? And if we continue, this effect will continue also. And even it is possible that the method will produce the same point twice and evaluates twice. Remember that function evaluation is a time-consuming operations. And this is obviously bad. And if we do 2 power n partitions, so we use not 1 hyperplane but n hyperplanes, the effect is the same. You see, almost all internal points are doubled. So there is a redundancy, and the same similar redundancy we have in bisection. So it seems that there is no possibility to avoid this redundancy. Of course, this is a very bad effect. Is it possible to do better? The answer is yes. Let us subdivide not on 2, but in 3 points, in 3 subboxes. Then what will happen? Look, suppose that we started to subdivide, we subdivide, and when we subdivide here on the next iteration, what happens that this point is exactly the same. And theoretically, we will be able to understand how this diagonal move in the multidimensional space. And when you do this, it is possible to go to the database of vertices and just to read the value of the function. So we have obtained this subdivision in 3 subboxes by evaluating the function only once. Because what do we want? We want to subdivide well to understand better the structure of the function, but we do not want to compute a lot. And here this is exactly the case. So there is a huge advantage, and if we continue, we will see that all the points have been read from the previous evaluation, and for each subbox, each value is used by 2 power n subboxes. So this is a very good usage of information. And in fact, if we consider the same function, there is no redundancy, and there is a huge acceleration of the search. I remind you the diagram of Jones and colleagues for subdivisions with on subboxes with the one central point evaluation. The question is it possible to use the same idea in diagonal algorithms? The answer is yes, but it is necessary to work a little bit. So here on the x-axis we have once again the half of the diagonal, and on the vertical axis we have two values now, and we have the sum divided by 2 of these values. Then if this Lipschitz constant is known, here we will have exactly the value corresponding to the minimum of the intersection of the cones. And once again, this means that we can use this representation for the intervals, and this is the best one. But if the Lipschitz constant is different, this is the best one. We again evaluate in intervals corresponding to the red points, and we can repeat the game. But we can do something more. Look, what do we have here? Here we have small intervals, small hyperintervals. So they correspond to the zones very well studied already, to zones of local minima. And what are these? This is a zone corresponding to unexplored huge intervals. So when you obtain the new promising solution, you go and try to improve it locally. When you have reached the minimal allowed diagonal and you do not want to explore more, what do? You go to the huge intervals, not consider small ones, and work on huge intervals. And so this also allows us, this idea has allowed us to improve and to accelerate significantly. And here you can see that just to show you what is the kind of problems we are able to solve, many local minima. Here there is this line that we start here, so we can construct this adaptive diagonal line going through the search region and then solve the problem. Okay, another idea is to Giuseppe Peano and David Hilbert, who have proposed a strange object, a space filling curve. Look how it is constructed. Nowadays, people use the word fractal to describe this kind of objects. So this is the basic figure. First partition, then it is substituted by this figure, by this figure, by this figure. As you can see, step by step, the figure fills in the space. Now, what can we do? We can take the starting point here and the finishing point here, and to stretch this curve. What we will have? We will have one-dimensional problem. And if the multi-dimensional problem was Lipschitzian, it is possible to prove that the one-dimensional one will be Hölderlin. And Strongen has proposed this idea in 1978. So we evaluate the function working on one-dimensional curve only on the curve. But this allows us to solve multi-dimensional problem by approximation. So you can see here red stars are points where we have evaluated the objective function. Here there is the global solution. Method has got the convergence to the global solution. And you can see that even though we evaluate only on the curve, we have obtained an approximation of the solution in the multidimensional space. Okay, obviously, all I am talking about can be done not only in 2 dimensions, but in many dimensions. And this is the idea. And Hölder minorant are not linear, clearly. And once again, as it was for diagonal methods, the question is it possible to use the ideas of Jones on the Peano space filling curves? The answer is yes, but once again, it is necessary to make a trick, because otherwise, here there is a mess. It is not possible which interval is best, because you see these minorands, they intersect one with another. But the question is in the metrics. Let us use Hölderian metrics. Then the whole figures become clear, and we can continue with the ideas of Jones and the company. Now, one of the questions that it is necessary to ask, which method is better than another? How to understand? For example, in math heuristics, people have test sets. Then they start to test and say, this method is better. But this is not good, because the solutions, there is a limited number of functions, and each person on 20 or 30 problems is able to tune parameters to say, my method is better. We said, this is not good. And we have created a generator that constructs classes of test functions randomly. You say dimension, you say the number of local minima, regions of the attractions, and you obtain 100 problems, but with all known solutions. So you know coordinates of each of the local minima, you know the values of each of the local minima, and you are able to test your methods easier. For example, if you have 100 functions in dimensions, which dimension? 5 dimension. Here we have Dirichlet, one of his variants, and our methods using piano space field curves. So what are these pictures? After 10,000 function evaluations, 10,000, so 1 million, sorry, we see that this method has solved 75 problems. This one has solved 85 problems, and this method has solved 100 problems. So all the problems have been solved. And here, this method has stagnation. It was not able to solve more than this problem. So visually, this is much better than to see tables. So if the characteristics of your method is higher and on the left, then your method is better. So obviously, I have shown this picture where my method is better. It is evident. Okay, so I was talking about these topics that can be seen in, for example, in this book. It is rather old, from 2000, but there were also already new editions, but it has 2 drawbacks. The first is weight. It weighs more than 1.5 kilograms, because there are more than 700 pages, and the second drawback is its price, that is higher. This book is smaller, and it is from 2013 with some of the new results. Okay, so let us talk about some applied problems. Recently, we work on these applied problems, and I will touch the first 3. So the first minimal root problem. Imagine that you have a signal that goes like this, and it can be non-differentiable. And when the signal crosses for the first time 0, something happens. For example, a door is opened, door is closed. Okay, engineers construct models and then try to find this point just by evaluating with the step epsilon many thousands of times in order to obtain this. And strangely enough, in electrical problems, it is possible very often to estimate the Lipschitz constant, because we are talking about the energy of the system. Because to have a pulsation, you need energy, and it cannot be infinite. So if you have an overestimate of the Lipschitz constant, what happens? You are able to construct this minorand. And look, we have evaluated the function 1, 2, 3, 4 times. The minorand here is above 0, so we are sure that here we have known the first 0 crossing point. So very fast. But also, if we have evaluated here and have got negative point value, here it is positive, also here we have known the solution. So very quickly we are able to close the solution. And if we are able to estimate the Lipschitz constant for the derivative, then it is even faster, obviously. So this is the first problem. The second problem is safe global optimization with noise. This is a very fresh problem. So we have a function f satisfying the Lipschitz condition, but unfortunately there is a noise xi that is limited by delta. And the problem consists that you need to evaluate the function only at the points where it is above the safety threshold h. Otherwise, something will happen. You can speak about, for example, of something atomic. Okay, you have a model, and if you evaluate in a certain point, there is an explosion. So you should choose for the function evaluation only those points where you are sure that it will be above the threshold. Okay. So at the end, since there is the noise, we consider this function j of x, f of x plus noise. And initially, people started to work like this. So suppose that this is black is our function. Then due to the noise, it can assume any of the values in this gray corridor. When this is the threshold, safety threshold, here you see that the function can go below the threshold, so this is an unsafe zone. And this also is an unsafe zone. So what people say, let us take, for some reason, from somewhere, a safety point, this one, x1. We construct the Lipschitz cone, and then we would like to understand which is the safe zone. We would like to enlarge this green zone, and then over this green zone to maximize the function. So people say, let us take and evaluate the function here and here. It seems to be a good idea, isn't it? But it is not. Why? Because if you evaluate here, the function due to the noise can be above here, and you go to the unsafe zone. Okay, and some explosion will happen. So it doesn't work. This idea doesn't work. When we evaluate in this point, it works, but here we are close to the border and everything is broken. We have proved that this function corresponding to, is not Lipschitz, but it is delta Lipschitz, where delta is equal to 2 times possible noise. And the algorithm should be constructed in this way. You evaluate the function here at this point, and then subtract to delta, and you construct this small cone and evaluate the function in this point. And then again, if you have got this, again subtract to delta and construct new cone. In this way, you are sure that you always will be in the safe zone. And you will find all these zones, as you can see on this example. We have found all this zone and we have tried to understand what is happening here. But this safe zone and this safe zone we have not found because the starting point was here inside and method is not able to go through the unsafe subregions. However, if it is a little bit, the threshold a little bit below, and here there is a very, very small space where to go, the method will find also this part. And then we can optimize, and the optimization will be done over only the same zone. So we have done many examples. For example, here we have 2 safe points, initial safe points in this subregion and 1 here. And we have found the whole safe subregion and optimized over it. And here we had no safe points, and we had not found, obviously, this subregion, and so on. Another problem is approximation and visualization of solutions to systems of nonlinear inequalities. Okay, suppose that all of them satisfy the Lipschitz condition, and here it is necessary to find not one solution, but all of them. Why? Because this is used in robotics. I will show in a few slides how. Okay, so clearly to find the whole the whole set of solutions is not easy, and Yevtushenko and his co-authors have proposed to use partitions to find these three sets, which one is for sure points belonging to this set of solutions, another one sure do not belonging, and in the middle points where it is necessary to continue to search. And they have used this kind of partitions. But remember that we have our Peano curves. And with Peano curves, it is possible to do better. You see that Peano curve go through regions, and here you see it is even possible to see, this is the magnifying of this part, what is happening. So these green points show points that are not in the set of the solution, and red one invites us to continue. Why this problem is important? Imagine that you have this planar robot, so this triangle, it is fixed in these points, and it is moved. And it is necessary to find the zone where it moves, in order, if there are other mechanisms, they do not clash one to another. So this is exactly the problem I was talking about. And we have used it using Peano curves, and you see this is that zone, the blue one, where this robot will move. In the green zone, it will not go. Here we have magnifying, and the red is the border where we can continue to explore if we like, if you like. And also it is possible to do this in multi-dimensional space. Okay, so up to now I told about this piecewise linear approximation of Peano curve, but it is possible to do better and use this non-univalent approximation having a very nice property. So it is constructed like this, okay? And what is the property? The property is that you can see that, for example, this point in the multidimensional space has three images on the curve, this, and this. And why this is useful? Because all of them correspond to one multidimensional point, but if we have computed one, we can simply read, as it was with diagonal methods, from the database and to put them there. And this also will accelerate the search and will allow us to obtain nicer pictures. So this is piecewise linear approximation of the curve. This is non-univalent approximation. And here you see the solution. The blue zones are the solutions. Okay. So now I would like to know how much time have I? 10. Okay. Okay. Perfect. Perfect. So I give just a small example related both to global optimization and to infinity computing, the next topic of the next seminar. So suppose that we have again Lipschitz global optimization problem in one dimension for simplicity, and there are some methods that are called strongly homogeneous. They are strongly homogeneous, for example, these methods, if they produce the same evaluations both for the function f and for the scaled function j of x with the scaled constant alpha and beta. Okay, so this is good in some situations. Let us go now to the computer and suppose that there is such a method strongly homogeneous. So now we would like to scale the function, and if on the computer we scale it with this small constant, then function is completely destroyed. So even though your method is strongly homogeneous, due to the finite and well-defined number of digits in the mantissa, function is destroyed completely. Even though if we want to return back, so I multiply this by 10 power 16, the result will be terrible. So this is an example of typical ill conditioning due to machine errors. Okay. So what is the infinity computing? Infinity computing is a new supercomputer that I have invented and patented in several countries that is able to work with different infinite and infinitesimal numbers. And here it is particularly useful. I show you. So this is the same function. And here there are points, you see, where the function has been evaluated by this method. Then we have another method, it evaluates in other points, and here another method. You can see that the last method is much faster. This method has made 465 evaluations, this, and here significantly. You can imagine that the last method, the best one, is mine, obviously. Otherwise, I would not show you this picture. Okay, but this is not important here because now let us solve the previous problem of ill conditioning using this method, this number. This is an infinite number with which the infinity computer works, and we can execute floating point operations on the computer with this number. And what do we have? Look, here we consider scaled function. It has been multiplied by one infinite number and added another infinite number. And you can see that the function is the same and the methods that are strongly homogeneous has evaluated exactly at the same point. So we have completely solved the ill conditioning problem in this case. And even if we here have gross 1, if gross 1 is infinite, obviously gross 1 power minus 1 is infinitesimal. So one scaling constant is infinitesimally small. This is infinitesimally large. The method behaves in the same way and the function has the same form. So this is one of the strong applications of the infinity computer, and on March 7 I will show you other applications. Okay, so you remember these operational characteristics, okay? So here you can see that the blue method is much better than other ones, okay? Now the question is, these methods are deterministics, but all meteoristics are stochastics. So how to compare deterministic method with a stochastic one? Because stochastic methods change their behavior. I remind you that here we have 100 problems. And what we have done, we have said, okay, let us solve these 100 problems 100 times and see what happens for these methods. 3 methods, okay? What happens? Here we have Firefly, and we have seen that it is true that these methods are stochastic, but it is not true that their behavior can be completely different. So here you can see that we solved 100 problems 100 times, and there is a zone that can be visible. So we can construct ideal best consisting of several characteristics and ideal worst cases, okay? And we also can see the average. So Firefly algorithms in average behaves like this on these 100 randomly generated functions. And now we can see that artificial bee colony method, gray, on these functions, its best performance is as average of the Firefly. So Firefly is better. And we also can compare it with deterministic methods. For example, the green method, you see, it behaves in average as Firefly in average. And these two methods are better when the budget, the possibility to evaluate the functions is huge. But if it is not huge, for example, genetic algorithms here, look, what happens? If the budget is small, then genetic algorithms works better than all these 3 deterministic methods. Why? Because genetic algorithms and meteoristics in general have very good tools inside incorporated to go to the closest local minimum. And if by chance, and you can see that this chance is more or less in 50 cases. this local minimum is the global one, then we are done. But then what happens? These methods have difficulty in solving harder problems where deterministic start to be. So I answered to the question, I said, what is better, meteoristics or deterministic mathematical programming methods? If your budget is small, probably it is a good idea to use meteoristics. If your budget is huge, it is a good idea to use mathematical programming methods, because then meteoristics can go to stagnation. Okay, and you can see that this visually, that is much better than to try to understand by the tables what is happening. Okay, so probably I stop here. Here we have another generation of functions with constraints. So we start with from these functions, then this is the global optimum, and then we start to introduce different kind of constraints. The problem becomes worse and worse. And so the global solution is this one, and these are really hard problems to solve. Once again, these are our books and some of other recent relevant references. Thank you very much for your kind attention.
Thanks for the excellent talk. Any questions?
Thank you very much. If possible, I have two questions. The first is, what is the status of your works with respect to manifold learning algorithms? And the second question is, so probably you know the works in quantum field theory by Migdal, who construct triangulations of surfaces, and maybe some things from that algorithm can be used in your ones and vice versa.
Okay, so I know that our algorithms are used in machine learning, but we do not do this. So we are concentrated on this kind of stuff. Also, in any kind of learning, we do not go there. But what we have noticed is that in learning, people use strongly Lipschitz global optimization, trying to reinvent the things that has been done 20, 30 years ago. But with manifold learning, I am not able to say anything. And the second question was with... So triangulations, once again, here I have shown you some simplices. This is the group from Vilnius working with triangulations. And triangulation, this is the following difference. There are different kinds of triangulations. So one is when you know something about the structure of your problem and you construct triangulation for this structure. Here, the problem is somehow opposite. So they use triangulation simplices in general in order to understand the structure of the problem.
Questions? Okay, I have two questions maybe. The first one is, does your method suffer from curse of dimensionality? Curse of dimensionality.
Okay.
In very high dimension, was how the...
So let us start with the first question. Yeah. So I always asked this question, but here the problem is not dimensionality, but the budget. Okay, budget of function evaluations, because there are problems where one function evaluation requires 1 hour. For example, in aeronautics. So in 1 week, you are able to do 200 function evaluations. So it doesn't matter what is the dimension. You have these 200 evaluations, okay? And that's all. So it can be 110, 2. So the main constraints is budget and not the dimension. But clearly, that if you go higher than 10 or 15 dimensions, these kinds of methods will suffer. Because, for example, just if you wish to evaluate in all vertices of the hypercube in 10 dimensions, this is 2 power 10. So what we are talking about. So people who say that we solved global optimization problem in 1, 2, 300 of, they do not use the word solve correctly from the mathematical programming point of view. Because solve from a mathematical programming point of view means that you are able to show that the solution you have found is in the epsilon approximation of the real global. Their solve means that they started from a known solution and were able to improve it a little bit or a lot.
Thank you. Yeah, my second question is about the question talking about noisy global optimization. What if right now you are talking about the noise is kind of bounded by data? I think it is small noise, right?
Sorry. Let I go in the slides and then hear your questions.
The data. Yeah.
Okay.
Do you assume how large the data can go? And what if we assume the noise is based some kind of probability distribution, can get the best bound or something like that?
So we have seen that people tried to do this, but they then made these errors that I have shown. So we just worked with noise that has a limitation. That's it. We did not apply any distribution because also with this simple, this is pretty heavy.
Yeah. Thank you. Okay. More questions? Okay. If none, let's thanks Dr. Sergeev again.
Thank you.